Hello, my name is Sriram and today I'm going to talk about deep learning. This video is split into two parts. The first part talks about the fundamentals of deep learning. The second part talks about a unique tool which can be used to implement deep learning techniques called digits. During the first half, we're going to explore the fundamentals such as neural networks, perceptrons, dropout, and other such fundamental concepts which are used for defining a deep neural network. In order to gain a better understanding of deep learning, we're going to explore a unique network called AlexNet. AlexNet was developed for the ImageNet 2010 challenge of classifying 1.2 million images into 1,000 unique categories. This network uses the concept of convolutional neural nets, which we will explore during the series of this video. The second part of the video deals with using a tool developed by Nvidia called Digits. The Digits tool is built on the Caffe framework and allows the user to simulate AlexNet and perform classifications on his or her dataset provided. So there are various forms of data such as tabular, audio, video, and images. Traditional machine learning techniques focus on classification and regression of this tabular data. These techniques have been optimized in order to provide the best and accurate result while consuming the least amount of resources to be worked on this tabular data. If we take the same techniques and try to implement them on audio, video, and non-traditional data sources, they often consume more resources and more amount of time. Therefore, there is a need for more efficient and less computationally intensive algorithms, hence the introduction of deep learning. So there are three popular definitions of deep learning. The first definition states deep learning is a branch of machine learning which uses a cascade of multiple layers in order to perform feature extraction and transformation. The second definition states that deep learning uses unsupervised learning methods in order to define and retrieve the multiple features to represent data. And the third definition talks about how deep neural nets use multiple layers in order to provide and extract the most important features and sub-features of a given dataset. In the following slides to come, we'll be discussing a few fundamental concepts of deep learning. The first major concept is neural networks. Neural networks borrow their idea and concept from neurons and from in biology. So a neural network, as depicted in the figure, consists of nodes, and each of these nodes are connected using links, and these links have weights associated with them. The values x1, x2, and up to xn are the input values in the input layer. Depending on the activation function defined in the neuron and the weights associated between the links between one neuron and the other, the values of x1 up till xn get modified in such a manner. In the given figure, there are three different hidden layers and one output layer. Based on our requirements, we can define how many outputs we want. In this example, we only specified a single output. There can be networks where you can have 2, 3, or up to m outputs. But the basic idea is that we want to provide n inputs and generate m outputs, where in most situations n is larger than m. In between, we have a collection of hidden layers. These hidden layers are responsible for extracting and compressing the information. As we can see, the second hidden layer has 3 nodes, while the first hidden layer has 4 nodes. So in this network, the first hidden layer expands the information and the second hidden layer compresses it down. A multi-layer perceptron is an extension of the neural network concept. A perceptron is basically a network which consists of a binary classification, either a 0 or a 1. When you say a multi-layer perceptron, it consists of multiple hidden layers which will constitute to a single output layer. A multi-layer perceptron is a very important concept, as a deep learning uses many such multi-layer perceptrons in order to provide feature extraction for the given data sets. Convolutional neural networks. Convolutional neural networks are a very popular form of deep learning. It uses a collection and a deep networks of multi-layer perceptron architectures. In this example, we can see the input is an image which is 32 cross 32 pixels. It is a signboard saying 60. The idea is that we are trying to use convolutional neural networks in order to extract the features, so at the end we get maybe 5 to 6 subcategories at the maximum, rather than having 32 square inputs. So the first layer, it consists of a multi-layer perceptron which scans the entire image using a 5 cross 5 filter. By doing so, it creates a feature map. The feature map is basically a subpool of the input image. This subpool of feature map is again passed through another convolutional neural network which is size 2 cross 2 and creates some more feature images which are size 14 cross 14. Because we are working on the same image and our filters are scanning the image row by row and column by column, there will be some redundancies between the consecutive frames or consecutive images. In order to remove these redundancies, we do subpooling or subsampling. Subsampling is basically combining these feature maps into a single output, which is like the average of these. There are a few popular techniques which are used, which we'll be explaining later on. Once this feature mapping is done and subsampling is achieved, it is then sent to a softmax regression and a final fully connected layer in order to obtain the classification of it. The softmax regression is popularly used for classification technique. So in order to gain a better understanding of deep learning, we explore a popular deep neural network called AlexNet. AlexNet was defined for the ImageNet 2010 challenge, which is basically used to classify 1.2 million images into 1,000 unique categories. These images are high-resolution images and require quite some computational power. Traditional datasets such as MNIST and Caltech 101 often lack the diversity of the images found in ImageNet. MNIST and Caltech often contain only a few categories, say 6 for MNIST, and Caltech 101 consists of 101 categories. So traditional neural networks might work in this aspect, but due to the ever-growing demand for larger and more performance-oriented networks, the AlexNet paved the way for this kind of learning. So AlexNet consists of 8 learning layers. 5 of them are convoluted layers and 3 of them are fully connected layers. The convoluted layers are responsible for the feature extraction, while the fully connected layers are your regular neural networks. The output of the final fully connected layer is a softmax regression, which is used for the classification. The main aspect of softmax is to take the results obtained from the fully connected layer and fit it to a probability distribution of 1,000 classes. The input image of the first convolutional neural network is a 224 cross 224 RGB image. The convoluted layer consists of 96 kernels, each of size 11 cross 11, and which is a stride of 4 pixels. Following the third and fourth convoluted layers, in order to provide normalization and improve the efficiency of the result, there are max pooling and normalization layers provided to it or added to it. So it performs a sequential model. This is the diagrammatical representation of AlexNet, which is in forming of a sequence. We have first the image which is going from left to right. At the extreme left, we have the first convolutional neural network. And at the extreme right, we have the softmax regression, which is denoted by a dense, and the results are the predictions or the probabilistic predictions for each of 1,000 classes which are to be determined. In the subsequent slides, we will be explaining some of the regularization techniques used in popular networks such as the AlexNet described in order to improve the performance and efficiency of the system. Max pooling. Max pooling is one of the most popular pooling techniques. It's a form of nonlinear sampling where, given in the single depth slice provided in the left hand side of the figure, we perform max pooling our filter size 2x2. So we basically create a 2D matrix of size 2x2 where we determine the maximum pixel value from that 2D matrix, and the 4 elements in that 2D matrix are now represented by the maximum element respectively. As you can see, in the 2D matrix 1, 1, 5, 6, the maximum element is a 6. So now in the maxed pool outcome, the 4 elements, that is the 2D matrix, is now represented as a 1D element as 6. 1D element as 6. Similarly, in the 2D matrix 2, 4, 7, 8, it is represented by 8, which is the maximum element in that set, and so on and so forth. So by doing max pooling, we reduce the overall computation required for the system and reduce the number of data frames generated at each and every convolutional neural net layer. Dropout is another interesting technique which is used for normalization. The idea is that a neural network consists of multiple nodes. In order to provide regularization and make sure the network is not biased towards a particular result, we need to perform random dropping of the neurons in a given network. This is performed by dropout. We specify the percentage of the neurons we want to drop, and the network randomly chooses these neurons and drops them. As shown in figure, on the left hand side we have the fully connected network. On the right hand side we have the dropped out neurons marked by X. So by dropping these neurons, we improve the overall performance and prevent bias and overfitting of the system. Every time or every iteration the network goes through, the dropout is performed, and the neurons which are dropped out is not fixed, it is randomized. So during the dropout phase, we prevent multiple neurons from getting dropped out consecutively. So now we'll be discussing about the popular applications of deep learning. So first we start with speech recognition. Apple introduced Siri and Microsoft introduced Cortana. Both are personal assistants provided on mobile phones. These personal assistants work by recognizing audio provided to it and feeding it to a deep neural network, for which the audio is converted to digitalized format and the corresponding results are fetched from the internet. For example, by using Siri, a person can search for the current temperature at the place he is located in. Next, NLP, text to speech. So by using deep neural networks, we can reduce the amount of time taken to convert text to speech and speech to text by a fraction compared to the traditional methods which we're using before. A popular domain which is rising up right now is deep learning and information retrieval. Information retrieval basically deals with extracting information or data from a large collection of files and documents. Traditional techniques involved using bots and web crawlers, but now we want to use deep learning techniques which will reduce the time and resources required compared to the previous methods. Object recognition in images has become really efficient because of deep learning. Deep learning has improved the way we recognize objects using convolutional neural networks, LSTMs, and RNNs. Object recognition can be often seen in virtual reality headsets, for example Google Glass, or in street cameras for pedestrian detection in order to prevent major accidents from happening. Event detection in videos is another popular domain where deep learning is being utilized. Let's take an example of a sports video. In order to detect major events in a sports video, we need to physically tag them. Rather than doing that, we can design or train a deep neural network in order to automatically detect such events. For example, when a 3-point shot is taken in a basketball game, rather than physically tagging it, the neural network will detect it automatically. Or in a cricket video, whenever a six is hit, we can automatically detect it rather than physically going and tagging it each and every time a six has been hit. And then this can later be used for summarizing videos as well. So this is a new domain as to where deep learning is being utilized. So after going through deep learning, we might think we need a high-end supercomputer in order to run these networks efficiently and quickly. Rather, we just need a high-end GPU which has enough CUDA cores, and you can run it on any platform. A popular library which are used for running deep learning are Theano, TensorFlow, and Keras. Theano and TensorFlow are basic Python libraries designed for running basic LSTM, CNNs, and RNNs. We as scientists have to basically determine the network parameters and the optimizations in order to get the optimal result. Keras is a new Python library which runs either on Theano or TensorFlow and uses QDNN in order to provide more optimization and better performance on our GPUs. Two popular deep learning frameworks are Caffe and Digits. The advantage of using Caffe and Digits are that they are frameworks, so they provide the entire complete solution to deep learning architectures. Rather than designing everything from scratch, such as in Theano and Keras, we can use Caffe and Digits which already have existing networks, and we can provide slight modifications to these networks to optimize for our problem set and data set. In the subsequent part of the lecture, we'll be going through Digits, which is provided by Nvidia, designed specifically for CUDA. In that video, I'm going to explain how the GPU is set up, what are the requirements for CUDA, and we'll be showing a small example as to how CUDA is running with Digits at the front end. So after successfully setting up your GPU, you need to log into developers.nvidia.com. There you need to provide your user credentials, and it will take about 2 to 3 days for Nvidia to authenticate yourself, after which you have unlimited access to certain Nvidia applications provided by them. In that, you need to search for Nvidia Digits and download Digits 3 or Digits 2.0. For this particular example, I'll be explaining Digits 2.0. Once you download it, you will be, depending on the platform you're using, you can download the zip or the tar.gxe file. In our example, I'm downloading the tar.gz file, and as you can see, which is highlighted in my downloads folder on my Linux platform. So I extracted my digits.2.0 gz file to my home directory. As we know, Digits runs on Caffe platform. So Caffe directory is an integral part of a Digits platform. Next, we open the terminal window and navigate to the Digits directory. Here, we are presented with as you can see, we have 3 shell scripts which are important for the Digits application to run. The first thing we need to do is run the install shell. Since I've already gone ahead and installed it, there's no point for me to run it again. But for fresh users, you need to run the script. This will take approximately 5 to 10 minutes depending upon the GPU clock speed. For this particular system, which has a Titan X 6GB RAM module, it took about 5 minutes. Next, we can run the runme.sh. As you can see, the Digits logo has started up, and the local file system will start up immediately. Digits starts running on port number 5000. You can now log into Digits through your web browser. Home page of Digits, we have the data sets and the models. The data sets is where we load the images, and the models is where we define the neural network. Here we choose images classification. Once we select that, here you can choose the type of image, whether it's a color or it's a grayscale image, the type of encoding, the appropriate resolution, and if it is a bigger size or a smaller size, a certain amount of transformations can be performed, and this transformation matrix can is determined by the users, whether it's squashing it, cropping it, filling it, or half crop, half fill. Next, we specify the folder as to where the image is located. We've chosen the 101 object categories, which is a unique data set where we have 101 different categories. Each of them contain about 3000 to 4000 images each. We specify the amount of validation and amount for testing. Next, we scroll down and select the data and we assign a name to this data set. Demo data 1.1. We go ahead and create this. So once we create demo.1, the images are loaded into the system's memory, and the GPU starts creating the training and the validation set. The train consists of 75% of the images, and the validation consists of 25% of the images, which are randomly selected. So there is no bias generated. As you can see, the categories are already specified in the data sets. For example, motorbikes is a count of 200 images, and similarly, motorbikes is a count of 599 images in the train set. We're given approximate validation images, training images, size, and all other information required here. It tells us the estimated time to be done, and how much memory is occupying in the given space. So in the home page, we can see the demo.1 has been loaded into the data sets. Here we are specified with the status and the time it took, which is about 2 minutes since it's a small data set. After which we need to load the model which will run on this dataset. This is done by simply clicking on images and classification and the mode tab. In the model, we specify the dataset which we want to load. Upon selecting the dataset, we find the metadata is populated. Next, we can choose standard networks, any previous defined networks, or our own custom networks. For this particular example, I'll be using a standard network which is AlexNet. And as already mentioned, AlexNet and its original paper can be viewed on clicking on it. Here we're provided with a brief abstract and the required fundamentals and links to the author's profiles. Next, we can even customize the AlexNet to our preference. Here, you can specify the data type or the crop size and the various parameters which can be tweaked in order to improve the performance for your particular data set. As you can see, all this is done using Caffe. So we need to be a little bit versed in Caffe's layout and architectural design, which doesn't involve much work as it is quite simple and straightforward to utilize. For example, let's take this convolutional parameter here. It tells us that the number of output kernels are 96 and the size of the kernel is 11 and a stride of 4, as already mentioned in previous presentation. This is the first convoluted layer. Similarly, we can define the activation function ReLU by just specifying layer name equal to ReLU, which can be defined on your own, but the type determines the activation function which is to be implemented. And bottom and top. Bottom represents what is connecting it, and top is from where it will continue to. Similarly, a normalization layer is provided. So like this, we can determine our own layers. If we want, we can also visualize these layers by clicking on the visualization icon. And here is the visualization. So we have the data, which consists of 4 batches. The data is then sent to the convolution layer and the label assigned to it. From con1 and goes to the ReLU architecture, then normalization, max pooling of size kernel 3, strike 2, one more pooling followed by another convolution layer. So the entire layer architecture is provided in a visualized format so we can maintain our hierarchical layers and determine what is being passed to another, and what are the input and output parameters being passed to them respectively. For example, the 384 is another kernel size provided to it, and 256 is also another kernel size. And finally, they all come down to the softmax regression without a loss. We generate the loss, and the accuracy is determined. The solver options, we specify the important parameters like training epochs, the learning rate, and what is the algorithm used to modify the learning rate and reach the optimal solution. Training epochs basically tells the number of times the given images are fed through the model. That is the number of iterations it has to run. In this example, we're going to choose 30. Next, we specify the snapshot interval, which basically determines at what time or intervals in the epoch should we take copies of the network. In this particular example, after each and every epoch, we're going to take a snapshot of it. The batch size is the size and number of images specified in a particular batch. By default, we're taking the network defaults, or you can specify on your own. Solver type basically is the algorithm used in order for the basic learning rate to be adjusted so that we reach the optimal solution. We can use a stochastic gradient, or we can use AdaGrad, AdaDelta, or Nestrovs. And next we specify the learning rate determines the pace at which the network will learn about certain images and classify them into the respective category. Initially we set it to 0.01, and using SGD or AdaGrad, the learning rate is modified until it reaches its optimal solution. Next, we specify the model name to be given, which is demo model 1, and we create it. On creating demo model 1, we can see the status of the training. Here we provide with the solver information, the data set demo.1 information, and the status of the job, when it started, and roughly how much time it will take. So it's saying estimated time is about 14 minutes 57 seconds. We can see the GPU memory utilization, its GPU utilization maximum, and the temperature of the GPU. We're using a GTX Titan, which is at #02. The present day digits can also run on multiple GPUs. So that's why we have a dynamic GPU usage monitor here, and we can see a graphical representation of how the training and the testing is taking place. The blue represents the training loss, and the yellow represents the accuracy of validation, and the green is used to represent the loss of validation. So you can see after each and every epoch the accuracy, its training, and the loss of training as well. As we scroll on, we can see the learning rate of each and every epoch and determine whether we are going the right pace or do we need to modify the epochs as such. Once the training has been completed, we can see the status as well as the time it took in order for training to finish. Now we can see the final accuracy, which is about 67%. We're getting less accuracy because we're trained only for 30 epochs. Rather, if we train a little bit more, we can get a better accuracy. Next, the validation loss as well as the loss in training are provided to us. Here we can see the variation in the learning rate of the given system as the epochs are increasing. In this section of the model, you can actually upload your image and determine the classification the system is giving, as well as you can upload a list or a collection of images for which the classification can be determined. Here you can specify the batch size of the images to be loaded and the number of images to be shown per category. So in order to test our model, we now upload a given image and see the classification the model gives. So we click on Browse, Pictures, select the image and upload it. Once we do that, we select Show Visualization Statistics. So this gives us the mean deviation, standard deviation of the given image, as well as the visualization of the image through the given convoluted layers. That is, the individual outputs of each convolutional layer is determined by using the visualization and statistical tools. Next, we click classify one image. Upon doing this, we get the predictions. There are top 4 or 5 classes are displayed, in this case 5, and we see it's a perfect match. Even though this image is not in the original training or validation test set. So we give this mean standard deviation, the output of coordinate 1, which consists of 96 filters, each of size 11 cross 11, then the output of the second convolutional layer, which focuses more on the image, and certain features are extracted. As you can see, some of the features such as the tires and the handlebars are being elaborated or fixed upon in certain frames of the given convolutional layer. As we go down, we go to normalization, which basically performs an intensity value correction. This is the output of the intensity corrections and the max pooling as provided. So in this manner, we can see the outputs in each and every layer provided to us in the given setup. So this is the advantage of using digits in deep learning environment, as it gives us a detailed overview of our network and the detailed overview of each and every layer on the given network provided for a given input. This brings us to the end of our lecture. I hope you have understood the concepts of deep learning and how to implement simple neural networks and deep learning techniques using a popular tool called Nvidia's digits. Hopefully you have understood deep learning better and can pursue and utilize it in your course and field of action.